Hello, hello, hello. Can the people in the back, is the mic reaching you guys? Sounds good? Excellent. All right, yeah, so halfway through, I'm gonna go through a demo. So just if you're interested in doing a demo, maybe start thinking if this is something you'd like to do. But without further ado, I'm excited to be here and to talk to you a bit about the research that I do here at the University of Toronto, and in particular, using these telescopes that we've built across North America, as well as across the globe, to study the universe in a way that maybe you haven't actually thought of in the past. So tonight's lecture is going to be all about exploding stars. Now, the topic of exploding stars, you might hear me say the word supernovae. And in this case, if ever you hear the word, or if you ever hear me say supernovae or supernova, all I'm referring to is the physics of a star that's exploding. So just as astronomers, we typically use this word supernova. So if you hear that, that's what I'll be referring to. So to start, many of you have probably thought about stars that have exploded, or I've heard at least the term supernova. But the actual process of what a supernova is, very basic, is you have a star that is about 6 times larger than our sun or bigger. And when it reaches the end of its life cycle, it undergoes a violent explosion, which we call supernovae. So in this case, we're looking at a simulation that was done by NASA that kind of gives you a picture of what it would look like in real time if a star were to explode somewhere nearby us. There's 2 things that I want to point out. So the first thing is that at the beginning of the animation, you can kind of see the shockwave that goes out before all this right now. So there's an initial blast wave that gets launched early on, but then after that, what follows is kind of all the material of that star gets ejected and left and pushed into the surrounding environment. Now, these supernovae are kind of, when we talk about supernovae, or if you talk to any astronomer, there's kind of one particular event that astronomers will always talk about, and they'll always rave about, and it's supernova 1987A. So astronomers are very clever, or very boring and lazy with how we name things. As when we talk about supernovae, we basically just say, what year did it happen? Was it the first one in that year? If it was, well, you slap a letter on it, A, B, C, D, go down. So in this case, this was the first supernova that went off in supernova in 1987, and it was actually detected by Ian Shelton, who currently works at the Dunlap David Observatory in just an hour north of here at the observatory up there. And so a Canadian-born astronomer detected this supernova, and it is notable because it is one of the most nearby supernovae, or the most nearby supernova that we have detected since modern astronomy has really taken off. So on the left-hand side, what you're looking at is a Hubble Space Telescope image of the supernova back in 1997, so about 10 years after the original explosion. And what you can actually see is kind of all these different rings that kind of indicate different things. So the rings are what you're looking at is that, if I go back to this GIF, or this animation, that shock wave that's expanding is actually the ring heating some material that was left over surrounding the star, and it's it's glowing in the optical. But at the center is kind of all that leftover material, that hot gas and that hot metals that have been kind of ejected into the environment. We revisited this supernova, or not we, but just James Webb went back in 2024 and took an image of that same supernova. And as you can see, it's still, even many, many years after the original explosion, it's still extremely bright because it's so nearby. And so astronomers kind of have used this particular supernova because it's so close by. We've been able to study the explosion, or the physics of these explosions, what kind of material is ejected into the environment, how does a star that is so big actually undergo a core collapse and explode to create these beautiful images. So it's been kind of a lovely staple event that we've used to study this particular type of physics. But you might be wondering, and as you're rightfully wondering, why do we actually care about studying these supernovae? So it's not, we don't just study these because they're pretty pictures, although I will say that the first reason, which I would say why we do actually care about studying these, is that they do result in some of the most beautiful images, in my opinion, of what we can find in the universe. So on the left, we've already talked about supernova 1987A, but it turns out that even when things explode thousands to tens of thousands of years ago, we can still see them really, really bright if we were to look at them now. So in the middle, what we're actually looking at is another star that exploded about 900 years ago that left behind this very, very beautiful remnant. So it's Taurus A, and it has this very beautiful optical image that was also taken by HST. And on the right-hand side is Cassiopeia A, which is another supernova remnant, or a star. It's kind of the remnant of a star that exploded about 300 years ago. And this was actually taken by an amateur astronomer, probably somewhere in their backyard, maybe not in the backyard. They probably went to a nice dark sky area. But these things are so bright many, many years after they exploded that we can take these beautiful images of them, and even with just kind of typical, kind of a very minimal setup, you can get these beautiful images of these different stars that exploded hundreds of years ago. All right, so maybe that's not enough to convince you. So what else do we care? Why else do we care about studying these supernovae? The second reason is that when a star it evolves through its life, it starts to build up a very large repertoire of metals inside of its core. And as we saw in that animation at the beginning, all that metal that was built up is kind of ejected into the surrounding environment. And so if you actually look at all the types of metals that are actually kind of coming out of the supernovae, it turns out that all of these heavy metals, so if you think back to your early chemistry courses in high school, you have your carbon, your oxygen, your iron, and your nickel. All these heavy elements are now released into the universe. Now this is important because here on Earth, we have all these different heavy elements that just are here, but we want to understand how it actually came to be that our solar system, how do we get all these heavy metals? All these things that are necessary for the functioning kind of existence of human life. We have all these heavy elements, but we don't exactly know how we got here. And so by studying supernovae, which is kind of your main mechanism to create these heavy metals and release them and eject them into the universe, we can start to understand kind of how, big picture, this can fit into kind of where all these heavy elements come from, which then lead to the building blocks of human life, which can then lead to, say, a formation of a planet, which then leads to the formation of life. And so it kind of fits into this bigger picture of the life cycle of humans and where we came from. And now if that's still not enough, then the final reason, which is kind of a reason that I have come to find super interesting, is that when you have these supernovae and you have a star that explodes, every single time that a star does explode, it will almost all the time leave behind what we call, or for a fancy word, called a compact object. Now the most famous one that you can probably think of is a black hole. So these are left behind after a star collapses in on itself. The gravity is too strong, so it forms this massive black hole. But in some cases, if it's not so big, it will form a different type of object. And in this case, you're looking at a zoomed in image of kind of this very energetic, special type of star. It's not exactly the same type of star as our own, but it's kind of a very exotic neutron star is what we call them. And they have these very extreme kind of physics environments that surround them. And so astronomers and physicists love studying these things because they offer kind of insight into some of the most extreme environments in the universe. And so we can kind of get particles that are accelerated to ultra-relativistic speeds, and it just is like a perfect sandbox for studying the universe in these very exotic regimes, known as a pulsar. And so in this case, it's basically a very special type of star that you can think of as kind of a big lighthouse. Now, the reason why why we call it a lighthouse is that it has this beam of light that is at the poles, and as it swings around, it eventually hits us here on Earth, and we can detect them, and we see this flash of light on our detectors. In the alternative case, you can get something that's like a black hole. Now, in this case, this is kind of an exaggeration of what you'd expect, but the reason why these are formed and these have these kind of very energetic regions surrounding the black hole, and I'll get to more about this later on in the talk. But all that to say, so hopefully at this point, you've got kind of convinced, or at least understand why we as astronomers study these things. But there's been a kind of a main thing or a caveat to all of these kind of images and these statements that I've said so far. So this telescope here that you're looking at is kind of responsible, which really pioneered the field of studying these supernovae. So that first image that I showed you of supernova 1987A, that was taken by the Hubble Space Telescope here. Now the Hubble Space Telescope is really good because it's, for things that are nearby, it can use the light that we see with our own eyes to study the universe in kind of the way that it sees the universe. The issue is that if you if you want to study these supernovae, the rate at which we can detect a supernova that's really nearby, such that Hubble can look at it and say, okay, I can see the rings of the supernovae, that's about once every 50 to 100 years. So the rate at which we can detect something that's close enough to actually study it in detail with Hubble Space Telescope is kind of too short of time, or it's too long of a time scale for astronomers to make meaningful progress in the field. And so what we have to do is we have to actually go to supernovae that happen in distant galaxies. So in this case, this is supernova 1993J. So it happened a couple of years after supernova 1987A. But this time, we no longer see these beautiful rings. And the reason for this is that this source is just too far away. So what we actually see is kind of just a smudge on our detector. So if you look at the bottom right, you can see that there's some light there. And we know that it got really bright there. But that's about all we can say. And so the question that I'm going to ask and that we're going to explore is, can we take this and can we zoom in even further? Now, to answer this question, we're going to have to backtrack a little bit. So I'm going to just walk you through a bit of context as to what we need to know to get to this point. So all the light that we've been talking about, especially in the context of the Hubble Space Telescope, surrounds the visible light spectrum. So that's the colored light. That's what we can see with our own eyes. If you go up to the telescopes later, that's the same type of light that you'll be looking through the telescope. Though I think it's cloudy tonight, but maybe it'll clear up. But there is much more light in the universe than just that of visible light. So you probably encounter light in different ways that you probably don't typically think of. So starting all the way at the end, you can see that there says X-rays and gamma rays. So if you go to the dentist and they take an X-rays of your mouth, they're using X-ray light in order to take images of your teeth. If you keep going down and you get past visible light and you get down to the infrared, things that glow very hot or things that are hot will glow in the infrared. So if your eyes were sensitive to infrared light and you turned on your stove and you looked at the stove, it would look like there's light coming off that stove. It's the same reason why night vision goggles can work as well, because things like our body heat, it glows in the infrared. And so when you're out at night, you can just see, if you had infrared or night vision goggles, you're just looking at infrared light emitted off your body. If you keep going down, you get to microwaves. So the light that we use to heat up our food in the kitchen, if you turn on your microwave, it's actually just shooting microwave light at your food to get it energetic, warm it up, and then it's ready to eat a minute later. But the light that we're going to focus on, and then I'm going to spend the rest of the talk talking about, is radio light. Now, radio light, the idea of radio light is probably something that is not super common, because you think of radio and you probably think of like sound and listening to the radio station and things like that. And it's true, you also encounter radio light on a day-to-day basis. And I imagine after this talk, you'll probably walk around and be like, oh, there is actually a ton of radio. So if you're walking down the street, and maybe not on the street, but if you start driving out to the countryside, I think there are some of these around in Toronto. But if you're looking at these are just cell towers. So our cellular devices, the way that we communicate here on Earth, we beam our signals up to these cell towers using radio light. That radio light then just gets transmitted. They beam it to somewhere else across the Earth. It receives it. They keep transmitting that light over and over, and then finally gets beamed down to the person that you're communicating with, and suddenly you've sent a text message. And so we're using this type of light that is very efficient at just transporting across long distances to communicate with each other. That's radio light. When you go in your car and you turn on the radio station and you look at and if you turn on the dial and you say 88.5 FM, that tells you the exact type of radio light that you're listening to, or that your car is receiving and transponding to. And so you can actually tune into to listen to the radio, because 88.5 FM is 88.5 megahertz. It tells you the frequency of the light that you're transmitting and talking with the station. Same thing with your Bluetooth. If you have wireless headphones and you're listening to your music, then the way that your AirPods or your headphones are communicating with your phone is through radio light. And so all of these radio signals, which astronomers we just use as radio light, or we refer to as radio light or radio waves, these permeate throughout the entire world, all over Earth, and are extremely useful. But what happens when we take this light and we kind of look for these same signals, but instead of looking here on Earth to communicate with each other, we actually point our telescopes and look up into the sky? This is what we end up finding. So what we're looking at here is a radio image of our galactic center. So if we look at the center of our own galaxy, maybe you've seen images of it in the optical, but when you look at it in the radio, it kind of reveals a lot of other things about our own universe. So at the center that you can see there, that's actually the center of, or is the supermassive black hole at the center of our own galaxy. And there's a couple things. So the first, where things are really bright and orange, that's kind of where there's the most energy. That's where there's a lot of things going on. It's very energetic. Things where it's bluer, it's kind of cooler. There's not too much going on. There's still obviously things happening. But what I also want to point out is that you can see kind of these weird bubbles kind of on the top left over here and in the bottom right. And these are actually the same supernova remnants that I was talking about early on, but as seen in the radio. So those bubbles that we saw at the beginning, those nice little images that we saw, this is what they look like in the radio. And so it turns out that our universe is also glowing all the time in the radio. And that's exciting because now we have this whole universe of things to study at different light that we don't see with our own eyes. Now for comparison, at the top right, this is kind of a zoom in of an area of what it looks like with the James Webb Space Telescope. So just qualitatively, if you're just looking at these two images, you can see there's a lot of differences. They don't look identical. There's clearly more points. They can see a lot more stars, whereas radio sees a lot more of the broader, it's kind of more zoomed out in that particular case. That's just due to the way that the images was taken. But there is they probe different physics, they probe different astrophysical objects. And so for that gives us kind of a lot of things to study in the universe, which is extremely exciting as astronomers. Now, the actual telescope that went and took that image that I just showed on the previous slide is this one, the Meerkat radio telescope. So this probably, if I'm, again, now saying, okay, if your picture of a telescope in your mind is that of something that you put looking through your eyepiece, which is what you would do if you go up to the top of MP later, that's not what we do here. In this case, radio telescopes are kind of, they have a bunch of different shapes, they come in a bunch of different shapes and sizes. So this particular one, you can see that there's a lot of these smaller, weird radio telescopes. And the way that it works is the radio light comes from the distant universe, it bounces off of all of these reflectors, and then gets focused to a central point. And that central point is then transmitted down to our computers, and we can process it and make the images that you see. But what you can see is that there's a lot of these individual dishes. And the reason that's important is that the purpose of radio astronomy is to create as big of a light bucket as possible. You just want something that can connect, or that can collect as much light as possible. And so what you'll see a lot of the time, this is a small component of what is now a multi-billion-dollar global project that Canada is a part of, called the Square Kilometre Array. And it is a project that is it's a combination of many countries across the globe building one of the largest radio telescopes in the entire that's ever been seen in human history, and it will study the universe in very, very exquisite detail. Now, that's not the only telescope. So if we go to China, they have what's called the 500-meter aperture spherical radio telescope, or FAST. So this is a radio telescope that's built in a valley in China. And if you can see from left to right, the distance between both sides, as the name suggests, is 500 meters across. So if you take 4 football fields or 5 football fields, put them down, or 5 soccer fields, put them down in a row, then you would get the length of just from one side to the other. And again, the reason that we do this is because the bigger the light bucket, this is quite literally just a big bucket to detect a lot of this radio light and focus it and detect very faint signals that we're interested in studying. And of course, here in Canada, and especially at the University of Toronto, the telescope that we work with is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME for short. This is a telescope that I've been working with for the past 5 years about, and my supervisor before me worked on it for 5 years prior. He was the original developer and builder of this telescope. And so early on, now that we've gone through all this background, we want to return back to this question of, can we zoom in even further? And so in order to answer this question, we went and talked about radio astronomy. There's probably going to be some relation to that. And I'll tell you that the answer is yes. But then the question is how? Now, rather than me spend kind of the next 5 minutes lecturing you on the physics of how this actually works, I figured this would be more intuitive if I were to do a demonstration. And so I'm going to turn on just the front of the lights. Oh, okay, that's bright. And I'm going to ask, sorry to flashbang you guys. I'm going to ask if there's 5 volunteers just kind of throughout the crowd. So if you're interested, you'll just have to stay in your seat or stand up. Actually, I've got one. If you want to raise your hand if you're interested. Okay, I'll take one at the back. You guys decide amongst yourselves. 3. Yeah, go ahead. So 1, 2, 3, 4, and one more maybe in this general area. 5. Perfect. All right. So if you've been named, if I could have just asked you to stand up really quickly, just so that you're out of the way of everyone. Amazing. Okay, so I have 1 there. Remember 2. I'm going to say 3, and then 4. Where's the 5th? 5-ish. Okay, yeah, there's a 5th. I'm going to say yes, back over there. So what I've done is in this room, we're going to simulate what it's like to actually zoom in on a radio source. But in this case, we don't have a radio source. Instead, we have sound. We have ears, which our ears are going to act as our radio telescopes, and the sound is going to act as the radio light. And so somewhere in this auditorium, I've hidden a speaker. Don't go looking for it, because it's not too hard to find if you do look for it. And what I'm going to do is I'm going to ask you to close your eyes. And when I'm going to play a sound, I have currently connected to the speaker, and I'll play a sound. And when you hear the sound, just close your eyes and point to where you think the sound is coming from. All right, so for all the volunteers, and then afterwards, we'll keep going from there. All right, so if you're a volunteer, just close your eyes. And I'm going to play a sound. I'm just going to move over to my... All right, get ready. All right, so if you're a volunteer, just please point to where you think the sound's coming from and keep your fingers there. Excellent. Okay, keep your hands up and go ahead and close or open your eyes. Okay, so we've got 3 hands over here that are pointing towards here. We've got 1 that's pointing over there. And then those guys up there that are pointing over somewhere back over there. Okay, so I will say, now what I'm going to say is that for everyone in the room, thank you guys so much. I'm going to say, everyone, I'm going to play the sound, point to where you think the sound is coming from. Okay, so I'm seeing consensus that somewhere over here is where the sound's coming from. And if I go ahead and show, it's indeed where the sound's coming from. So that's great. Now, you might be wondering, why was it when we did with 5 people, it wasn't as accurate, or maybe people were bouncing, saying different directions? It's completely normal. The way that sound bounces around the room, it will reflect off the walls and cause you to hear it coming from a different area. But when we added everyone, you guys ended up finding that the sound was in agreement generally from this general corner of the room. Thank you guys so much. You guys can sit down. Thank you. Yeah, sure. Give them a round of applause. Amazing. Okay, I'm going to turn the lights back off. It's going to get dark again. Amazing. All right, so what did we just do? What was this exercise all about? So somewhere in this room, I hit a speaker. We then asked kind of our audience members, our initial 5 audience members, to pinpoint where they thought the sound was coming from. Now, as we saw, when we had a couple people, there is maybe some general agreement from some people on one side of the room, and then maybe other people thinking it was from a different area. But when we added everyone in the room, suddenly we were very good at pinpointing and zooming in on where that sound was coming from. It turns out that if you do the exact same thing but with radio light, it behaves the exact same way. So if you replace all of our ears with radio telescopes, and then you replace the sound, which in this case was just a speaker playing bird sounds, with a source of light that emits radio waves, then we can actually figure out where that radio light is coming from. But the important thing is that first, if you have more radio telescopes, the better you can figure out where it's coming from. You have more sensitivity to that sound. You start to see where other people are pointing, and you'll be like, oh yes, I think I agree that it's coming from there. And then all these telescopes will be like, okay, in general, I think the source is coming from there. But the important thing is that when you actually take a telescope and you have 2 that are side by side from each other, they don't do as well of a job of determining where that light was coming from than telescopes that are super far away from each other. The same way that if I take 2 people from across this room and I'm standing in the middle of the room and I'm talking, they can point, when they point to where I'm standing and because they can hear me, it's kind of like X marks the spot is where, and it'll be more highly precise than a bunch of people standing in the middle saying it's somewhere from the front of the room. And the same holds true for radio telescopes, where if I go back and forth between 2 telescopes that are close together, they're like, yeah, it's somewhere around here. But if they're far apart, then they're really, really good at pinpointing exactly where that sound is coming from, which is also why when we had the entire lecture hall, and people on the side, you get a wide variety of range of people, then you can start to really zoom in on where that sound is coming from. So the technique that we just demonstrated here in the lecture or in the lecture hall, but when we apply it to radio astronomy, is called interferometry, or in this case, very long baseline interferometry. So now what we've done, instead of just taking people in an auditorium hall, we instead take people and put them across the globe. And these telescopes, in this case, instead of people, we're going to put radio telescopes, and very sensitive radio telescopes. And in doing so, what we can do is we can actually zoom in on things that are very, very far away, that even if they're super small, we can still make out small details. So the example that I like to give is that if we put a hockey stick up on the moon and it was glowing in the radio, we'd be able to make out specific details of that hockey stick on the moon just by it residing there on the moon, which is an extremely powerful tool. That means that suddenly things that are very, very far away, we now have a technique that allows us to zoom in and take very high precision images of these sources. Awesome. So we have this supernova 1993J. It's an M81, which is about 11 million light years away. What does it look like if we actually use this technique of VLBI? And so I'm going to just play what this looks like, and I'll walk you through what we see afterwards. Amazing. So what you're looking at here is a composite or a movie of this particular star that exploded in 1993, or at least the light arrived to us here in 1993, imaged over the course of 30 years using this technique of very long baseline interferometry. And so the light that you're seeing is actually radio light emitted from this interaction of this blast wave that's kind of expanding away from the original star. It's heating up a bunch of material. And as you can see, the areas where it's nice and red is where it's glowing hot. There's a lot of energy there. And things where it's dark, there's kind of a lack of energy. This was done by Norbert Bartel, who is a faculty at York University, so just an hour north. And this work is extremely impressive because over the course of 30 years, we now have this nice detailed, we can study the physics at which the actual shockwave expands and gives us a lot of insight into, well, now suddenly we have a technique that we no longer need to study supernovae that are in our own nearby universe, but we can start to look at things that are happening in distant galaxies. And that's extremely powerful, and we no longer have these tiny little smudges, we have these beautiful rings that we can use and study a lot about our own universe. Now, if you take this technique and you push it to the absolute extreme, at least so far that we've been able to achieve here on the Earth, then you get this famous image. Now, I imagine many of you have seen this image. This is a radio image of a black hole in a nearby galaxy. And what we actually ended up imaging is a supermassive black hole at the center of M87. And so the center is actually where the black hole is, and the ring around it is the event horizon. So kind of all of this material that is kind of falling into the black hole glows very, very hot in the radio. And that's kind of what we were able to image. And all that, you can see that in the middle, there's absolutely no light that is able to escape. And that's just because due to the black hole that's at the center, there's no light that's able to go beyond the event horizon. So it's a very, very powerful technique. It's a very, very powerful tool that allows us to take these very, very high precision images, zoom in very far into these extreme environments. Now, the final thing that I want to talk about for the next about 10 minutes is a topic called fast radio bursts. Now, I imagine maybe some of you have heard about these, but for those that haven't, fast radio bursts, or abbreviated to FRBs, again, astronomers are very clever. They're fast because they last less than 1,000th of a second, so about 10 times faster than you could blink your eyes. So if you just blink your eyes, divide that by 10, and that's roughly the duration of which these events are happening. They're radio because they happen in the radio, as the name suggests, and then finally they're bursts because they are kind of on for a bit and then they turn off. And in this case, the amount of energy that they're releasing in a single burst is equivalent to the amount of energy that the sun outputs in a single day. So they're very energetic. There's a lot of energy contained in these single bursts. Now, it turns out that these fast radio bursts are kind of happening all over the sky, everywhere, in all directions. But the issue is that as astronomers, we don't actually know what's happening. We see these things, we see these blips in our radars, in our telescopes, but we don't actually know what's going on, what's actually causing these. And the question is can we actually use this technique of very long baseline interferometry, or VLBI, to figure out and better understand the origin of these bursts? And the answer is, of course, if I ask that, then it's probably yes. And so a large portion of the work that I do here at the University of Toronto is actually commissioning and building these new radio telescopes to kind of study and understand and unlock kind of the next step of studying these mysterious bursts. And so the CHIME telescope, which I showed earlier, the one that's built in British Columbia, we've built 3 new telescopes across North America. And throughout, when I finished my undergrad at McGill, and also as I began my grad studies here at the University of Toronto, I've kind of gone to all of these sites and been able to actually go in and plug in the antennas, help build the system, make sure that the telescopes are working. And that's kind of my lead role in this. But there was one particular event, just to kind of showcase the capabilities of these telescopes, to kind of give you a sense of what VLBI can allow us to do to study these weird bursts that could be related to exploding stars, but we're not entirely sure. Back about a year ago now, almost a year ago, in March of 2025, we detected an extremely, extremely bright burst at the CHIME telescope. So it kind of fell into this weird patch of the sky that was where CHIME was super sensitive. And what you actually detected is something that looks like this. So to our telescopes, this is what these fast radio bursts look like. So on the x-axis is just the time, so how long this burst actually lasts. You can see that suddenly it's like kind of noise, and then all of a sudden it's very, very bright, and then it goes away. You can see that also at the top, where you just see this bright spike at a particular point in time, and then it disappears. And the thing is that these bursts, they go off one time, and then they never happen again. And so we've been trying to understand. We get one opportunity and one chance to figure out where these things are coming from. The issue is that CHIME by itself, it does an okay job at figuring where this thing is coming from. And so if you ask CHIME, okay, where did that burst? You just detected that burst, where did it come from? It says, probably it's somewhere in this galaxy. Now that's not particularly useful. Like that'd be like saying, okay, we sent a signal out and someone says, oh, it's somewhere in the Milky Way. It's like, okay, well, there's a lot of space to look at in the Milky Way. It's not particularly helpful. So then can you actually zoom in and say, well, if you could tell me which solar system you're in, well, then that is more useful. Now, I'm not saying that we're doing the exact same thing, but that's kind of the guessing game. And so to answer this, we have these telescopes which are built across North America. We have the telescope. We have a telescope or 2 telescopes in British Columbia, one in Northern California, and one in West Virginia. And so using this separation of all of North America, we now go from an image that looks like this, where CHIME says, okay, this is where the galaxy is, to now suddenly pinpointing exactly where in that galaxy that burst is coming from. And so now for the first time, because these things only happen once, we only get one chance, this capability has never been capable before because it's just extremely difficult to, if you don't know where to look, an event goes off, you now need to pinpoint where it's coming from. It took a lot of years of development to get to this point. But we now have this ability, and we were able to say exactly where that burst was coming from. Well, now suddenly, there's a lot of telescopes that are not radio telescopes, like the James Webb Space Telescope, like Hubble, that are really good at taking really nice images of these environments. So then what we did is we went and slapped James Webb Space Telescope, and we looked at it a very long time at this particular location, and we found a whole lot of nothing, which is unfortunate, but is kind of the nature of science. We don't exactly know what's going on. We have some better ideas as to what's going on. We think it's some special type of neutron star, some star that's formed after a star explodes, but there's still an ongoing debate, and we need a larger sample. And so the work that I've been doing has been to kind of build that sample, to use these telescopes to establish hundreds to thousands of these little zoom-in images so that we can get a better idea of what is actually creating these bursts in the first place. And so I hope that now that I've gone through this exercise of VLBI, you now have insight into a technique that as astronomers, we use this not all the time, but as a kind of a novel technique to allow us to take very zoomed in pictures of things that are exploding, that are bursting, and I hope that you now have a better insight into that. And I want to thank you all very much for your cooperation during the demo, and I'm happy to take any questions. Thank you so much. Let me turn on the light.
Yeah, sure, maybe turn on. Yeah, so thank you, Mattias, for the great
for your
talk.
eyes. It's coming on.
Yeah, prepare yourself. Woo! Hi, everyone. Good morning. Okay, so now we're going to be taking some questions. Please raise your hand if you have some questions. I'll start right here.
Hi. Does your radio telescopes work with a cloudy sky?
Yes. So the question was, do our radio telescopes work with a cloudy sky? And the answer is yes. So we actually can observe during the daylight and also at the nighttime, which is really nice. So optical telescopes, you need to wait for the sun to go down because the sun is just too bright. But it turns out that if you go to the radio, as long as the sun is far enough away from where you're looking, then you can still see the universe just fine. You do lose some sensitivity because the sun is still very bright in the radio as well, but it doesn't completely make the sky disappear. And the same thing goes for clouds. Clouds, radio light can easily pass through them, and whereas in the optical, you're not able to. So it is a nice thing where even if it's cloudy outside, it's rainy, we do lose some sensitivity, but we can still see through them, and it allows us to observe 24/7 all the time, which is really nice. Sophia's going to be moving around the mic.
So this technique works really well with radio.
Yeah.
Would this also work with normal light, just because it's still using the same kind of focusing or being able to pinpoint? Essentially, they're the same type of waves, right?
Yeah, it's an excellent question. So can we do the same technique of separating, say, two optical telescopes by 1,000 kilometers and combine the signals? So the answer, the short answer is no, just because there is a fundamental limit in physics that stops us under some conditions. I won't go into too much detail into that one. There is ways to do it if you have telescopes that are close enough, a couple hundred meters apart, I think is kind of the limit at which optical telescopes can do this. But there is a limit. There's an underlying physics that stops you from being able to do this. The reason that we can do it with radio is that the behavior of radio light is very similar to waves instead of individual particles. And that ends up allowing us to do all this funky stuff where we can combine signals from across the globe. But yes, that is an excellent question.
Cool. Here.
Hi there. So I have a question. You were talking about fast radio bursts.
Yeah.
Are they in any way related to the to pulsars?
Excellent question. So the question is, are fast radio bursts related to pulsars? The answer is both yes and no. Pulsars are kind of similar. The main difference is that pulsars happen all the time. So they are formed, a pulsar is a neutron star. It was that lighthouse that I was showing. Here, let me bring it back, just so that I can, while I'm talking about it. Oh, I think it just died. We ran a battery, and right there. Okay, so this was an image or an animation of what a pulsar looks like. Now what you can see is that these pulsars, they're continuously spinning. They have this beam of light. So when they come across our view, we see this blip in our radio telescopes. And you're entirely right that they are similar. They have a similar profile. They kind of look the same to our telescope. The difference is that these ones happen regularly. They always are coming back to us and hitting our telescopes over and over. But the fast radio bursts, they only happen once and then they never happen again. And so even if they are spinning, there's some mechanism that's stopping them from being able to have light on continuously. They're also, so that's one reason. And then the second reason is that the amount of energy that is emitted by FRB is much more than a pulsar. So pulsars are within our own galaxy. All of these other bursts that we're detecting are from other galaxies. So the fact that we can detect them here on Earth means that they have to be releasing more energy for us to be able to detect them. Otherwise, they would be too faint. But they are closely related, yes. Oh, sorry, Sophia. I'm just following the microphone.
Yeah, sorry, I'm coming to the side of the room now.
Yeah, that ring that Let's Go
Yeah.
is that star is doing something, pulling in a little. Its gravity field's pulling in a little too much matter.
Yep.
And that ring is holding it together like a magnetic ring.
Mm-hmm.
But now there's too much mass, so it destroys the magnetic ring. And so those four elements are sprayed out.
Yep.
But they're also compacted down inside the black hole even more.
Yeah, so what ends up actually happening after the star explodes is not fully understood. We have some ideas of how kind of these heavy elements either fall back onto the black hole, and there are some models that predict that you have all this material that you just released and you formed a black hole. Some of that material will fall back onto that black hole and generate kind of these weird magnetic fields that you're talking about. But it's not fully. We don't have a large enough kind of sample of sources that we've actually detected things actively falling back for us to be able to say for certain. But it is definitely a theory that exists and that is kind of well accepted within the field.
Okay, we'll do 2 more questions. I'm gonna come all the way to the back. Can you project your voice? Perfect, if you could hear.
Thanks so much for the demonstration.
Of course.
I'm curious on how's the data aggregated. So as an example, if let's say it's only North America.
Yep.
You mentioned 4 satellites before.
Yep. Yep.
How often is that data aggregated, and where is it? And like, where's the central hub?
That's an excellent question. So if I go, yeah, I'll repeat the question. I'm just gonna bring up the image of. Sorry, there's so many slides. This guy. Okay, so the question is, we have all this data from all these telescopes. How often and where do we actually combine the data together? Because of course you're separated by thousands of kilometers. So how do we realistically actually combine this data to figure out where these things are coming from? The way that we do it is currently this network that is used here actually takes the individual data that was recorded at each telescope and ships it or flies it to a central processing site. So if you use the network that's in North America, it gets shipped to Socorro, New Mexico, which is where their correlation center is, or where they process everything together. And this happens. So at each of the sites, they record their data kind of during the observation, and then maybe a couple days later, they'll pack it up into a shipping container and then just send it over. If you use the European network, what they do is they have their central processing unit is in the Netherlands. And the same thing, they have telescopes that are in all over Asia, that are all over Europe, that are also in South Africa. And then sometimes you can even combine signals that are in Australia, and all of those dishes get concentrated, or get all that data gets shipped to one particular spot in the Netherlands, processed. But it's like the amount of data that we're talking about is like hundreds to thousands of terabytes. It's very expensive data. Radio telescopes are very expensive for holding data, but that's kind of the general process of how it's managed.
Okay, one more question.
There's one very very eager one.
So yeah,
Yeah,
I have the
yeah, that's
microphone,
great.
but if you can just project your voice.
Yeah, considering the distance between the supernova and Earth,
Yeah.
diameter of the Earth is not negligible, like almost a point, and all these telescopes are on one point.
Oh, I see what you're saying. Yes, except that light also, depending on what type of light that you use, it will stop looking like a point. It's kind of like a weird answer, but it's just it's as if it's kind of going back to that example where everything's just at one spot. How do you actually figure out where the thing is coming to better precision? But it turns out that the Earth is big enough that we can actually zoom in and use. It doesn't fully look like a point at the light that we're looking at, which is maybe hard to believe, hard to picture. But I understand why it's kind of weird, but it is a large enough distance that we can actually do this, which is cool. Awesome.
Okay, so let's thank Mattias one more time for his excellent talk. Perfect, and I'll lend it over to you, Abigail. to go over some info